Look at this little student table. Every row records a student ID, a name, and a department. And notice something quite but important. Wherever the student ID is the same, the name comes out the same too. Rows 1 and 3 both hold student 1 and both say Ravi. Fix the student ID and the name is forced. That kind of promise is the heart of this lesson. We write it with an arrow. Student ID determines name. Read that arrow as a rule the data must obey. Any two rows that agree on the left must agree on the right. This is a functional dependency, the exact notion that keys and good table design are built on. Let's pin the meaning down. Columns on the left we call X. Columns on the right we call Y. X arrow Y says, in every valid table, any two rows equal on all of X are equal on all of Y. The left side, X, is the determinant. Let's test two rules on real rows. Does student ID determine name? The two rows with student 1 share the same left value, and the name matches on both, Ravi and Ravi. So this rule holds. But does student ID determine department? Same two rows, yet one says CSE and the other EE. Same left, different right. A direct violation. So student ID arrow department does not hold. Two flavors worth naming. A dependency is trivial when the right side is already inside the left, like A and B together determine A. Always true tells you nothing new. The interesting ones are non-trivial, where the right side brings in something genuinely new, like a determines B. Those are the ones we chase. Given a few dependencies, many more follow for free. Armstrong's three axioms generate every one that must hold. Reflexivity is the obvious one. If y is part of x, then x determines y. You already have it. Every trivial dependency is just reflexivity in disguise. Augmentation lets you carry extra baggage. If x determines y, then adding the same columns z to both sides keeps it true. X with z determines y with z. The keyword is the same z on both sides. And transitivity is the chain rule. If x determines y and y determines z, then x reaches all the way to z. Student ID determines department. Department determines its head. So student ID determines that head too. From those three, a few shortcuts fall out. Union combines to right sides. Decomposition splits one apart. And pseudo-transitivity chains through a larger left side. All handy, but all just consequences of the original three. Applying axioms by hand is fiddly. One clean tool answers almost every question about dependencies. The attribute closure. The closure of a set X, written X plus, is every attribute that X determines directly or through a chain. The algorithm is a simple loop. Start the closure as just X. Then scan your dependencies. Whenever a rule's entire left side already sits inside the closure, pour its right side in. Keep sweeping until a full pass adds nothing new. To guardrails. The closure only ever grows and can never exceed the table's columns, so the loop always stops. And you need the complete left side inside before a rule fires. Half of C2D is not enough. Let's make it move. 5 columns, 3 dependencies. A gives B gives C, and C and D together give E. We'll compute the closure of A and watch the set grow. Start the closure of A as just the set containing A. Nothing has fired yet. This is our seed. A is inside the closure. So A gives B fires. Pour in B. The set is now A, B. Now B is inside too. So B gives C fires. Add C. The set grows to A, B, C. Can we go further? The last rule needs C and D together. We have C, but no D anywhere. And nothing gives us 1. So C and D gives E is blocked. It cannot fire. A full sweep now adds nothing, so we stop. The closure of A is exactly A, B, and C, 3 columns out of 5. Now the twist. Compute the closure of A and D together. Seed it with both. Watch what that spare D unlocks. As before, A gives B, add B. Then B gives C, add C. We hold A, D, B, and C. That second rule chained in, so C has joined. The set is A, D, B, C. And here is the payoff. This time we have both C and D. So C and D gives E, is finally allowed to fire. In comes E. The set now holds every column. A full sweep adds nothing more. So we stop. The closure of A and D is all 5 columns. Same rules, but one extra starting column carried us all the way to everything. Why compute a closure at all? Because it answers the 2 questions you care about. First, is a dependency X arrow Y implied? The test is simple. X arrow Y holds exactly when Y is a subset of X plus. Back to our example. Is a arrow E implied? A plus is just a B C, no E there, so no. But AND arrow E, that closure was everything, which contains E. So yes, that one is implied. The second job is finding keys. A set of columns is a super key exactly when its closure is the whole table, because then it determines every column and pins down a row completely. So A and D together is a super key. Its closure was all 5 columns. Alone is not, since A plus stopped at 3. That single test is the bridge to finding candidate keys. Let's run one all the way through. 5 columns, P through T, 4 dependencies. First task, the closure of P. Seed with P. P gives Q, add Q. Q gives R, add R. Now P, Q, R unlocks P and R gives S, so S joins. Finally, S gives T, and T comes in. Every rule chained into the next. So P plus is all 5 columns, which tells us P is a super key, determining everything on its own. Second task, which of these follow? Since P plus is the entire schema, P arrow R, P arrow S, and P arrow T are all implied. Every right side sits inside it. And P and R gives T. By transitivity, P and R gives SS gives T. So P and R gives T. One last idea, tidiness. 2 sets of dependencies are equivalent if they force the same closures. Among all equivalent sets, we want the leanest, with every scrap of redundancy stripped out. That is the minimal or canonical cover. And it passes 3 checks. Every right side is a single attribute. No dependency is redundant, and no left side carries an extra attribute. A quick reduction. Take 3. A gives B, a gives C, B gives C. Is a gives C pulling its weight? Cover it up and check. Under the other 2, A reaches B and B reaches C. So A already reaches C without it. So A gives C is redundant. Cross it out. What remains, A gives B and B gives C, is a minimal cover. It is equivalent to the original set, but carries no dead weight. Your turn. 4 columns, A through D, and 2 dependencies. A gives B and B gives C. Pause the video and compute the closure for yourself. I'll wait. Here's the walkthrough. Seed the closure with a A. The rule A gives B fires, so add B. Now we have A and B. Then B gives C fires, so add C. The set is A, B, C. Anything left? No rule has C on the left, and D never appears on any right side, so nothing can pull D in. A full pass adds nothing, and we stop. The closure of A is A, B, C. If you got that, you have got the whole method. Trap 1. The big one. A dependency is a rule for every valid table, not a pattern you happen to see today. If two rows share a value by luck, that is a coincidence, not a dependency. The rule must hold for all data the schema will ever allow. Trap 2. Partial left sides. A rule like CND gives E needs both C and D inside the closure before it can fire. Just C is not enough. Miss this, and you add attributes you were never entitled to. Trap 3. Stopping too soon. Keep sweeping until a full pass adds nothing. Chains like a gives B, B gives C gives D need several rounds. Quit early, and your closure comes out too small. And trap 4. A reminder. X arrow Y is implied precisely when Y is inside X plus, and X is a super key precisely when X plus is the whole table. Almost every dependency question is a closure in disguise. Let's lock it in. A functional dependency X arrow Y is a promise. Rows that agree on X must agree on Y in every valid table. Armstrong's three axioms, reflexivity, augmentation, transitivity, derive every dependency that follows from the ones you were given. The attribute closure X plus gathers everything X determines. Start with X, keep applying rules whose left side is inside, and stop when a full pass adds nothing. And that one set answers both questions. A dependency holds when its right side is inside the closure, and a set is a super key when its closure is the whole table. Master the closure, and dependencies hold no mysteries.